what we are looking at is quantum states of electromagnetic field. So yesterday, remember, we started looking at number states. Or Fock states. So if I consider so now as I mentioned, we are looking at one mode of radiation, which means one propagation direction, one frequency, and one polarization direction. So if I propagate along z-axis, and if I have a x-polarized beam, and I have at a certain frequency, so that's one mode. So we are looking at just a single mode, and when I write, for example, if I write n, this means that the state is excited to the nth eigenstate of that single mode. So each radiation mode is like a harmonic oscillator, and the harmonic oscillator states are nth states. The nth state has an energy n plus half h cross omega. And so we are looking at one of the harmonic oscillator, which is one of the radiation field modes, and in that mode I am looking at a state in which the excitation is in the nth state. So yesterday we calculated the expectation value of electric field, that's 0 for the state, and towards the end we also calculated expectation value of E square, and that is h cross omega by epsilon 0 v into n plus half. We use the operators for the electric field and calculate essentially psi e psi and psi e square psi. So for this state, the expectation value of E is 0, expectation value of E square is h cross omega by epsilon 0 v into n plus half. Actually, you can also calculate expectation value of x and y, the quadrature operators. What will be the expectation value of x? Remember, this is n a plus a dagger by 2 n, which will be 0, because a acting on n is gives you n minus 1, a dagger acting on n gives you n plus 1, which is orthogonal to n state. X square n, so 1 by 4 a plus a dagger into a plus a dagger of n. So this is 1 by 4 n a square plus a dagger square plus a dagger plus a dagger a. Now can you find out and tell me what will be the value of x square expectation value? A square will give you 0, a dagger square will give you 0, a dagger can be written as a dagger a plus 1. So I will have 2 a dagger a plus 1, and a dagger a acting on n gives you n. So I have expectation value of x square will be 1 by 4 of 2n plus 1, which is equal to half of n plus half. Yeah? No, x is the is a plus a dagger by 2 defined. The quadrature operators are defined as a plus a dagger by 2 and a minus a dagger by 2i. The time and space dependence is separately sitting in the electric field expression. Okay. Similarly, you can show that expectation value of y is 0 and expectation value of y square is half n plus half. expectation value of y square will be n minus 1 by 4i a square plus a dagger square minus a dagger minus a dagger a of n. Minus 1 by 4, right? There's a minus sign coming from here. Okay, so this is a dagger a plus 1. So you will get essentially 2n plus 1 here with a minus sign, and you will get essentially half of n plus half. So we define variance of a quantity. For example, delta x square is x average square, x square average minus x average square. And because x average is 0 and x square average is half n plus half, so the variance in x is half of n plus half. And similarly, variance in y is also half of n plus half. So variance is something like, it's because of noise, fluctuations, because the value is not well defined. So when you make measurements of the observable corresponding to x, you don't get a precise value every time. So you take an average is one quantity, and then variance. How much is the variation around the average? So this is the statistical quantity that tells you how much is the fluctuation. The larger the variance, the larger is the fluctuation of the quantity. In fact, let me calculate, for example, the variance in the number operator in the state. What do you expect? So expectation value of number operator will be n. What is the number operator? A dagger a n, which is equal to n. A dagger a acting on n is n ket, so this is n. What about n square? N a dagger a n. So delta n square is n square minus n average square, because this is a state with a well-defined number of photons. The number of photons is exactly n. And so there is no variance. Variance is 0. What is the probability of finding n photons in the state? 1. Okay, suppose I take a ket 10 state, the probability of finding 10 photons is 1. The probability of finding 3 photons is 0. Probability of finding any other number of photons is 0 because the ket is ket n state. So there is no variation, fluctuation in the photon number because I am taking a state which is a well-defined ket n state. What I find is the electric field expectation value is 0. There is a variation in the electric field. In fact, I can calculate what is the variance in the electric field. So delta E square is equal to h cross omega by epsilon 0 v into n plus half. E square average minus E average square. E average is 0, so delta E square is h cross omega by epsilon 0 v n plus half. So this is a state in which the number of photons is precisely defined. The average value of electric field is 0. The variance in the electric field is given by this expression, and the variance in the two quadrature operators are given by half of n plus half. Please remember, we are looking at a state in which only one mode is excited. All other states have 0 excitation. The single mode state. I am having just a state in which there is excitation in only one mode, and all the others are in the vacuum state. Yes, Mohit.
Sir, in this particular n-ket state, We have an energy which is n plus half h cross omega, and expectation value of this is 0. This energy, if we measure the expectation value, it comes out to be 0.
No. Expectation value energy. Let me calculate. How do I calculate expectation value of energy? Expectation value of energy is how much? N plus half h cross omega. Because expectation value of energy is expectation value of n plus half into h cross omega. Because energy is n plus half h cross omega. N vector, n operator. Okay. Okay. So now there are some pictorial representations which are used to sort of describe this. Now we must take those pictures a little more carefully because they're not true representations of these quantum states. But for example, there is a picture in terms of plotting how the expectation values of the two quadrature operators. This is a pictorial representation of the expectation values of the two quadrature operators. Okay. Now let me calculate what is the, because it's a plot in terms of x and y, let me calculate the expectation value of x square plus y square first. Okay. So let me go back here. So let me calculate x square plus y square. So this is n a square plus a dagger square plus a dagger plus a dagger a, that is x square operator, plus y square operator. So that is minus 1 by, so okay, so 1 by 4 comes out with a minus sign. So this is a minus a dagger square. So a square minus plus a dagger square minus a dagger minus a dagger a. This goes off and I get 1 by 4 n. So this a dagger is a dagger a plus 1. This is a dagger a dagger a, a dagger a, a dagger a. There is a minus sign, there is a minus sign here. So I'll get 4 a dagger a plus 2, which is equal to 1 by 4. 4n plus 2, which is equal to n plus half. Actually, x square plus y square is, this operator x square plus y square is nothing but a dagger a plus half. So the Hamiltonian is h cross omega into x square plus y square. Okay, because it's x square plus y square operator is 4 a dagger a plus half. If I take the 4 inside, x square plus y square operator is a dagger a plus half, and Hamiltonian is h cross omega into a dagger a plus half. So this is nothing but, so Hamiltonian is related to x square plus y square. X square plus y square is an operator which is related to Hamiltonian. Hamiltonian is h cross omega into x square plus y square operator. So this is a state in which x square plus y square is precisely defined because a dagger a is precisely defined. The variance of a dagger a operator, which is a number operator, is 0. So x square plus y square is precisely defined. X is not precisely defined because expectation value of x is 0, expectation value of y is 0, but x square plus y square is well defined. So I can draw a figure like this. The value of x and y which I will get will lie on a circle of radius square root of this. So if you prepare an ensemble of identical states in the nth state, each one measures the value of x square plus y square, all of them will get n plus half. Because if you calculate the variance in x square plus y square, it will be 0 because x square plus y square is nothing but related to A dagger A, and I know that the A dagger A operator has no variance, 0 variance. So, if I take an ensemble of n-ket states, each individual measurement will give me precisely the value n plus half, okay? But the value of x if I measure, I will get different values, and on an average it will be 0. Similarly for y. So, you can see here the different points on the circle actually correspond to different sets of observations, and you will get some sets of x and y such that x square plus y square is precisely n plus half, but average value of x is 0, average value of y is 0. So, this is one way of representing this particular quantum state, n-ket state. The smallest circle you can obtain is corresponding to n is equal to 0, which is the vacuum state, and that is a circle of radius half, raised per half, 1 by root 2. The variance in the electric field or in the quadrature operators keeps on increasing as you go to higher and higher Fock states, because it is proportional to n plus half. The variance in E square is the variance in E is proportional to n plus half. The variance in x and y are both proportional to n plus half here and here. So, the lowest variance you can get is in the vacuum state, and that corresponds to an variance in electric field which is h cross omega by 2 epsilon 0 v. That is, if I use this equation with n is equal to 0 for the vacuum state, I have the minimum the minimum variance in electric field is h cross omega by 2 epsilon 0 v for the n-ket states. All higher order n-ket states, states having larger number of photons, precisely defined photon number states, will have larger and larger variance. Now, there is another way also of looking at this fact that the average electric field is coming out to be 0. There is another picture that I can draw. If I were to position myself at a certain value of z and measure the electric field, because average value of electric field is 0, what I will actually get is each observation will be different phases. This is field. This is one pictorial representation of the fact that each observation gives me, for example, at t is equal to 0, if I measure, I can find anywhere from here to here. So, in that sense, the state has no well-defined phase. If I take identical set of n-ket states and I measure the electric field of individual of the states of the ensemble, the average electric field will be 0 because each person's phase is different. But all of them have, if they measure the number of photons, they will all get exactly n. If they measure x square plus y square observable, they will get exactly n plus half. Okay, so because this is an interesting representation, because we will, when we go to other states like coherent states and squeeze states, we will get back to this kind of representation and try to draw similar pictures corresponding to that to get a better understanding of what the various variances and expectation values could mean. Okay, so this is these are n-ket states, and as I was mentioning yesterday, it is very difficult to produce states, single mode states with well-defined number of photons. What people can produce is multi-mode states, which I will come to a little later, which means it's not a single mode, which is I have to consider many modes together, but still having one photon. But this n-ket states form a very good representation because they form a complete set of states. You can represent any state as a linear superposition of the n-ket states. Okay. So now let me go one step ahead and let me take another state which is still a single mode state, but in a superposition of two nkets. So for example, I want to look at a state this is a state, again, I'm not writing any subscript, this is one particular mode corresponding to one particular frequency, one polarization, one propagation direction. So it could be propagating like this along z direction, polarization is vertical, and the frequency is omega. But the state is not a well-defined nket state, it is a linear superposition of two nket states. Okay, now what is the state? What is the probability of finding no photons? Okay, because the probability of finding no photons is, which is half. The probability of finding one photon is also half. And the probability of finding any other number of photons is 0. Because if you take n psi with n not equal to 0 or 1, you will get 0. So this is a state in which it's a linear superposition of a 0 ket state and a 1 ket state. So please note, I have an ensemble of identical states in this, and each observer measures the number of photons in that state. Some people will get a value 0, some people will get a value 1 with equal probabilities, because I have chosen 1 by root 2, 1 by root 2. I could have chosen alpha and beta, and with the condition that mod alpha square plus mod beta square must be equal to 1. Okay, normalization condition. Okay, now let's look at some interesting let's look at some interesting aspects of this. So let me calculate what is the expectation value of the number of photons in the state. So this is psi a dagger a psi. Okay, what do you expect? Half, because there is half probability of getting no photons, half probability of getting one photon. So the average will be half. Okay, so you can actually calculate. So this is 1 by 2 of 0 plus 1 a dagger a into 0 plus 1. So this is bra psi here, with the 1 by root 2, this is ket psi with the 1 by root 2, and then there is a dagger a, and so this is half 0 plus 1. A dagger a on 0 is 0 plus a dagger a on 1. 1, that's all. So this is half. So 0 ket on 1 is 0, and so I'll have just 1 1. Right? So that is the expectation value of the photon number. Please note, expectation value need not be an integer or half integer, it can be anything. It depends on the values of alpha and beta. But if you measure the number of photons in any superposition state, you will only get integer values, because any state will be written as a superposition of various nket states with different probabilities. So if you calculate, if you find out how many photons are there in that state, you will always get an integer number. But the expectation value of the number of photons, average number of photons, can be anything. Okay? So this is an interesting state. This is a superposition state, and you can form actually, even in a single mode state, you can form so many different kinds of superpositions. Because actually this is the most general single mode state, as we wrote in the first day, is essentially Now I want to look at states which are in a limit looks like classical states, which means I want to look at a quantum state of a single mode still, a single mode radiation state, because I know if I have an electromagnetic field in a single mode, I expect the electric field to vary as E is equal to E0 sine omega t minus kz. An electromagnetic field, a linearly polarized electromagnetic field propagating in free space along the z direction at frequency omega will have a certain amplitude E naught sine omega t minus kz plus phi some phase. And I know that in certain limits, the quantum states, quantum analysis, quantum mechanics should give me the classical analysis also. So I must look at states, those states which will then give me a representation of the classical states, which quantum mechanical representation of the classical states. And there are some states called the coherent states, which we will discuss now. Incidentally, these states were proposed by Roy Glauber in, way back in the early 1960s, and he got the Nobel Prize in 2005 for his work in quantum optics area, essentially. Quantum theory of optical coherence. He has developed entire quantum theory of optical coherence, and he introduced these coherent states at that time. And these states, as I will show you, are states in certain limit will look like classical states, and these are the states that a well-stabilized laser produces. The output from a well-stabilized laser, a quantum description of that is a coherent state. Okay, so let me introduce these coherent states. So these states are, so let me look at some states like this. I look at some states which I call alpha ket, and these kets are eigenstates of this operator. Now please note, A is not a Hermitian operator, so alpha need not be real. Okay, alpha can be complex because that's A is a non-Hermitian operator and A alpha is equal to alpha alpha. So this is an eigenvalue equation for the operator A, and I want to find out this alpha ket states in terms of the number representation, the Fock state representation. So let me write, let alpha be equal to I want to find out the values of Cn.
That they satisfy also still.
No.
They will be like the classical thing.
No, I want to find out what is those set of Cn's which satisfy this equation. I'm expanding alpha into alpha is some state which I say it's an eigenstate of the annihilation operator. I want to express alpha state in terms of ket n states expansion, and to do this I need to get the expansion Cn so that this satisfies this equation.
And what's so special about the coherent state?
I will show you that the coherent states in one certain limit will look exactly like classical electromagnetic waves, and they will have minimum noise, the noise of the vacuum state. So there are a couple of properties of these states which are very important states, and it so happens that lasers produce this state. The output from a laser is in a coherent state. So what I'm doing is I want to look at states which are eigenstates of the annihilation operator, and I expand because n-ket states form a complete set. I can write any state as a linear superposition of the n-ket states. So I want to substitute this into this equation to find out what are the values of Cn. So if let me substitute this here, A sigma Cn n is equal to alpha sigma Cn n. So this is equal to sigma Cn an is equal to alpha sigma Cnn. Now what is A times n? Square root of n minus 1. Okay, so let me expand this sum. So C0 term will be 0 because n is equal to 0. So I will have C1 0 plus C2 under root 2 into 1 plus C3 square root of 3 2 ket plus so on, which is equal to alpha times C0 0 ket plus C1 1 ket plus C2 2 ket and so on. In these sums, n goes from 0 to infinity. So I've just expanded the sum and written explicit terms. Now note, if I multiply both sides by bra 0, I will get C1 is equal to alpha C0 because all other terms will vanish. So what I'm essentially stating is the coefficients of the 0 ket on both sides must be the same. Coefficient of n ket state must be the same on both sides. So C1 is alpha C0. C2 will be equal to C1 by alpha C1 by root 2, which is equal to alpha square by square root of 2 into C0. C3 will be alpha C2 by square root of 3, which is equal to alpha cube by square root of factorial 3 into C0. And so on. So in general, Cn will be alpha raised to the power n by square root of n factorial into C0. So I've just formed recurrence relations and finding out the value for Cn. So I can use the Cn in the expansion for the alpha ket, and what I find is ket alpha is equal to C0 sigma alpha raised to the power n by square root of n factorial into n. Now what should this alpha satisfy? Normalization. So I should have alpha alpha is equal to 1. So this implies mod C0 square sigma n sigma m alpha star raised to the power n by square root of n factorial alpha raised to the power m by square root of m factorial into n m. Please note there is a product and I need to use two different indices for the summation. So bra alpha is written as sigma n is equal to 1. Bra alpha is written as sigma n alpha star raised to the power n by square root of n factorial bra n into C0 star. Ket n is given by this, and so if I multiply this, so this is what? This is delta nm. So this is mod C0 square. So one of the sums goes off. So m must be equal to n. So I get sigma n. Alpha star raised to the power n into alpha raised to the power n is mod alpha raised to the power 2n by n factorial is equal to 1. What is this? Sigma n mod alpha raised to the power 2n by n factorial. Exponential mod alpha square. Exponential x is a sigma n x raised to the power n by n factorial, which is equal to 1. So this implies, apart from a phase factor, C0 is equal to minus apart from a phase factor. I can always have another phase factor sitting here. So that is the value for C0. So I can substitute the value of C0 here to get a complete expression for the alpha ket. This is a linear superposition state of infinite number of n-ket states. The example we looked at just before this was a state in which there were only two n-ket states which were superposed, 0-ket state and 1-ket state. This is a state which has contributions from all n-ket states from 0 to infinity, and each one has an amplitude given by exponential minus mod alpha square by 2 alpha raised by n by n factorial. Now, for this state, I can calculate various quantities. For example, let me calculate what is the probability of finding n photons in the state. Can you tell me what is the probability? The probability of finding n photons in the state is mod n alpha square, Pn. How much is that? So, in fact, this n and this is the n is summed over. So, this I could write m here. Okay. So, only one of the terms will survive. So, I will have exponential minus mod alpha square mod alpha square raised power n by n factorial. Okay, n alpha mod square. So, one will be alpha star raised power n into alpha raised power n. So, mod alpha square raised power n divided by n factorial. What is this distribution? It's a Poisson distribution. So, if you prepare an ensemble of identical alpha ket states with a certain value of alpha, then, and if you do experiments on each one of those ensemble to find the number of photons in that state, each person will get a different number of photons, and that will be a distribution which is the Poisson distribution. And what I will show you, I think we'll have a quiz now. What I will show you in the next class is that this particular state, we will calculate the expectation value of the electric field in the state. And I will show you that this electric field expectation value behaves very similar to the electric field of a classical electromagnetic field. But it is different from a classical electromagnetic field because a classical field, you can precisely define the electric field amplitude and phase. Here you will find that in general it's not possible. This particular state has actually what is called the minimum uncertainty in that state. Okay, this is the state we were discussing in the class. we did not calculate what is the expectation value of the electric field in the state. Remember, in the nth state, we found the expectation value was 0. So I want to find out what will be the expectation value of the electric field in the state.